we're going to be going over MAST, which stands for Merkleized Abstract Syntax Trees. So this is a proposed addition to the Bitcoin protocol that basically allows for smaller transaction sizes, increased privacy, and larger smart contracts. So let's dive into the problem first. We have unused script data. So Nakamoto gave users the ability to write programs or scripts that act as dynamic public keys and signatures. So when you specify a script, the consensus enforces the Bitcoin protocol to not allow anyone to spend your coins unless it's returned true. So another aspect of that, though, is that these scripts allow for encumbrances. And encumbrances are specific restrictions on the script. So for example, the transaction must be signed with a private key. So the biggest problem that derives from all of this is that currently all script data must be written on the blockchain in their entirety. So if you have 5 encumbrances or if you have 50 encumbrances, every single one of those currently needs to be written on the blockchain, no matter if you're just using part of the script or all of the script. So yeah, basically any unused encumbrance data is going to increase the transaction size, reduce privacy, and basically limit your smart contract size. So MAST seeks to remove the need to directly include unused parts of the script on the blockchain. So to give a little background on the origins of MAST, it comes from abstract syntax trees and Merkle trees. So if anyone's unfamiliar with these, abstract syntax trees, here's a picture of it, is basically a way of describing a program by splitting it into individual parts. And it just basically makes it easier to analyze and optimize. And then Merkle trees, on the other hand, allow us to verify that any individual element is a member of a set without actually having to look at the entire set, and the entire set doesn't have to be present. So basically, with a Merkle tree, all of these member pieces get hashed up the Merkle tree, and as you get up the tree, you get to this Merkle root. And if we can verify that the Merkle root is true, we can therefore assume that any of these member pieces are also true, or valid, if you will. So to give an example of MAST, we're going to use Alice, Bob, and Charlie. So let's say we have a script that basically says Alice can spend her Bitcoin, but if she doesn't spend it within 3 months, so if she hasn't spent any Bitcoin in 3 months, then Bob and Charlie are allowed to spend her Bitcoin. So currently, in the current state of Bitcoin, we would need to store all of this logic onto the blockchain. What MAST would allow us to do is only write the pieces on the blockchain that we actually use. So in this first example here, we can see Alice is spending her bit, and it's just going to put 100 bytes onto the blockchain every time she spends her bit, and that's it. And we don't see this other side of the script. Then in the other piece where Alice hasn't spent her Bitcoin and it's been 3 months, Bob and Charlie are allowed to spend the Bitcoin. And in this example, we don't see any of the other side of the data. So this side that allows Alice to spend, we only see the piece of Bob and Charlie being allowed to spend. And that's the only piece that gets included onto the blockchain. So as you can see with the legend over here, this doesn't get written on the blockchain, this piece would. So what this allows us to do is it gives us 3 main benefits. The first one is smaller transaction sizes. So here's a graph that shows the number of scripts and the byte sizes. So as we increase scripts without MAST, we're going to start increasing exponentially logarithmically, the number of byte sizes that are going to be on the blockchain. But with MAST, we're either going to be sitting at this best case scenario, which is only going to be 100 bytes. And again, that's where Alice is just spending her Bitcoin. Or we're going to slightly increase as we get more scripts with as things get more complicated. But again, as you can see, we're never going to get anywhere near up to these higher byte sizes. The second thing it allows us to do is increase privacy. So in either situation, you have no idea what the other restrictions are because only one piece is getting written on the blockchain. Now, in theory, someone could go back and trace these transactions to see potentially what the other side was, but this is a much better solution than what we're currently dealing with. And again, if there were pieces, any party that was trying to track down what was actually going on here, they would never know if they found all of the pieces in like all of the encumbrances. So it still has a huge benefit in that sense. And then finally, it allows us to write larger smart contracts on blockchain. So Bitcoin has 3 different byte-sized hard limits that apply to individual scripts depending on the encumbrance construction. So Bear and SegWit sit up here at this 10,000 level, and then P2SH sits slightly below 1,000. And if we're using MAST, we are never going to hit the with MAST, we cannot exceed the byte limit in either of these scenarios. So that's another huge benefit that we can see with using MAST. So to summarize all this up, the main takeaway is the real achievement of MAST is that it allows Bitcoin users to create more advanced smart contracts without placing the worst case burdens on Bitcoin nodes. So currently, there are 2 MAST proposals. There's BIP 114, which basically uses SegWit extensions to allow native SegWit addresses to commit to the Merkle root of MAST encumbrances. And then spenders can then select a single subscript from the tree. And then there's some unnumbered Bitcoin improvement protocols that are being issued or that are being proposed by Mark Friedenbach, I believe is how you pronounce his last name, and basically would allow programmers to write scripts that can themselves validate MAST based on encumbrances. So basically both of these could be implemented with a soft fork and add the provided benefits that were outlined. So that is, in summary, what MAST is. Does anybody have any questions?
First of all, awesome presentation. I learned a lot. I get the benefits of MAST. I get the concept, but my only question is like, where is this information being stored and who's validating it? Like we have all these encumbrances or subscripts or whatever we want to call them. Where is that information maintained? I'm guessing it's off chain somewhere.
So,
or am I not understanding?
Honestly, I might not have the best technical understanding of this. My understanding, though, was that it was all stored in the Merkle root, but that
gotcha. No,
very well could not be the case.
No, that's the point of Merkle roots is you can hash down like a lot of information.
Yeah, that's okay. That's what I thought. So I believe it's all getting stored in the Merkle root.
Okay, and then you just publish the Merkle root, and then if you need to prove any of these encumbrances happen, you can prove up like you were talking about.
Exactly. Yeah.